In this video, we're just going to talk about some vocabulary from chapter 10. I'm making this video special for you, Jiyoung, so that way we can talk about chapter 11 without going through all the sections in 10. So this is coming from section 10.2 and 10.4, and it's just some terminology we need so that we can do chapter 11. Okay, so first things first, they have some terminology about how we connect vertices, in particular in undirected graphs. So two vertices U and V in an undirected graph G are called adjacent or neighbors. Such an edge between them, we call that E, and it is called incident with U and V. We say that E is said to connect U and V. So we use the word connect a lot rather than most of the rest of them. The set of neighbors in a vertex denoted in a V is called the neighborhood of V. And basically it's denoting all the vertices connected to that vertex. All right. And then the degree of a vertex is the number of edges that connect that vertex. A loop, however, does count twice for a degree. So we do give a special denotation for a degree when we have a loop. Okay, let's look at an example. So let's say we have these two graphs. They're undirected, right? They don't have any sort of direction. And let's list out the degrees and the neighborhoods. Okay, so here, let me give myself a little space here. So for G, here, I'll just kind of divide this in half. So for G, the degree of A is going to be 2 because A is connected to F and B. So its degree is 2. So those are the two vertices it's connected to. Okay, let's look at B. B is connected to A, F, E, and C. So it is a degree of 4. Looking at C, C is connected to B, F, E, and D. So it's also 4. Actually, here, let's be smart. Let's list all the degree 4s together. So degree C is also degree 4. And actually, I can see that degree F is also degree 4 because it's connected to A, B, C, and E. A, B, C, E. So it is also degree 4. All right. So I'm not going to draw all the highlights from here on out. I'll just say them just because I don't want to have to keep erasing. Okay, so let's see. Let's pick up then with degree D if I'm kind of trying to go alphabetical. D would be 1. It's only connected to C. We already did. Okay, so E. E would be connected to C, B, and F. So that's 3. And then here I'm going to put degree of G. It's not connected to anything. So its degree is 0. And that is a possibility. Okay, now let's look at all the neighborhoods for this. So A, it is connected to B and F. So I'm just going to list those two vertices as its neighborhood. Okay. B is connected to A, C, E, and F. I'm trying to write it in alphabetical order. It doesn't matter. You don't have to write it in alphabetical order, but we're trying to put some order here. I'm going to have to zoom out to put the next one. Okay, so for C, C is connected to B, D, E, and F. D is connected to just C. E is connected to B, C, and F. Oops, I'm sorry. I bumped a button and it got mad at me. B, C, F. F is connected to A, B, C, and E. Oops. A, B, C, E. And then G is not connected to anything, so we'll write the empty set for that one. All right, let's do the next one. This one goes a little quicker. So the degree of A, we're going to count all of the edges that are away from A. So in this one, it has this edge, this edge, this edge, and this edge. So 4 edges total. So the degree of A is 4. Okay, now B is special because it has a loop, and loops count twice. So it has A, E, D, C, and the loop. So that's 4 plus the loop is 6. C is just 1. D has quite a few because there's 3 right here next to D on the left. So 1, 2, 3, 4, 5. D has 5. E has several as well. Let's see. 1, 2, 3, 4, 5, 6. I'm counting 6 for E, and that's it. Okay, now let's do the neighborhoods for A. It is B, D, and E. And if you want to pause the video and fill this out and see if you got the same as me, that would be fine. B, okay, you count its own loop, okay, just so you know. So it's connected to A, it's connected to itself, it's connected to C, D, and E. So it's connected to every vertex, including itself. C is only connected to B. D is connected to A, B, and E. And then E is connected to A, D, and B, or B and D, if I'm going alphabetical. A, B, D. And there you go. All right, let's look at paths. So the informal definition of a path is it's a sequence of edges that begins at a vertex and travels from vertex to vertex along the edges. All right, that's how a path works. It's how you can get from one vertex to another, what edges you would need to take to get there. The formal definition, a path actually has a length depending on how many edges you actually traverse. And you indicate the path by the sequence of vertices. All right. So a few notes. A path is simple if we denote this path by its vertex sequence. Oh, sorry. When the graph is simple, we denote the path by its vertex sequence. The path is a circuit if it begins and ends at the same vertex. A path or circuit is said to pass through the vertices and traverse the edges. And a path or circuit is simple if it does not contain the same edge more than once. Okay, so let's look at this, and I'm going to state some interesting facts about this. Okay, so let's say we go from A to B to C to F to E. Okay, so that's a path. So let me write that down. So I'm going to do like little bullet points. So A to D, oops. Didn't give myself enough room. A to D to C to F to E. Okay, so that's a simple path. And because 1, 2, 3, there's 4 edges, its length is 4. All right, let's do another one. Let's do a circuit. Okay, so here, let's go B, C, F, E, and then back to B. Sorry, I lost my train of thought. So B, C, F, E, B. So that, oops, is a circuit. And it would be length 4. Okay, here, let's not do a circuit. Let's do, let's see. A, B, E, D, A, B. So here, you couldn't see my last highlight there. So A, B, E, D, A, B. So that is a path of length 5, but not a simple path. Okay, and then let me write down this sequence. D, E, C, A. So D, E, C, A. That's not a path. And the reason it isn't a path is we can't connect E and C. E and C don't connect. There's no edge between them. Okay, there you go. So there's kind of the basic terminology of paths and some of that vocabulary associated with it. And here's where it leads us to this idea of connected. So an undirected graph is called connected if there's a path between every pair of vertices. Okay. So which of these graphs are connected? So like start at a vertice and see if you can get to all the other vertices. So here, I'll just start at A and I can get to B. I could get to C. I can get to D if I just keep going, or an E if I keep going. I can get to F if I go this way. I could get to G if I keep going, right? A is connected to everything else. And I could do that for all of them. So A, or this graph, this is connected. This one, however, is not. So they say it's disconnected. You could just say not connected. And it's not like, for instance, A has no path to F, right? They're not connected. All right. A, that's A, not path to F. Wow, that's terrible. A has no path. There we go. To F. Sorry. All right, there you go. There's some vocabulary we need. Go ahead and watch now the videos for chapter 11.